Like all thrilling games throughout history, today's thrilling game begins with the selection of a positive integer. For our purposes, let's keep it small. Let's say we pick 4. The game is then played on a random permutation of the first 4 positive numbers. By permutation, we just mean an ordering of. So, for example, 1, 2, 3, 4 is an ordering of the first 4 positive numbers. This would in fact be what we call the identity permutation, because every number is in its natural location. But of course, we could have a more exotic permutation as well, like 4, 3, 2, 1, or even 2, 4, 1, 3, if you dare think it. Let's say we get the permutation 4, 2, 3, 1. Here's how the game works. We begin by counting from 1 at the very first card, or the very first number. So I'll count 1, 2, 3, and so on, but I want to stop once the number I count matches the card that I'm on. 1, 2, I would stop immediately here. When this happens, we get to remove the card, and then count once more from 1, beginning on the next card. 1, 2, then we loop back to the start, 3, 4, and at this point, we realize we're doomed. My next number is 5, and I'm just going to keep going up, and I'm never going to get to remove another card again. So this would be what we would consider a loss. We haven't won because we haven't removed all of the cards. So that particular permutation was not a winning one. But to see an example of a winning permutation, let's try this game with the permutation 1, 2, 4, 3. Again, we begin by counting from 1 on the first card. In this case, my count, 1, immediately matches the card, so we remove it. We go again, counting from 1 on the next card. 1, 2, 3. 3 matches this card, so we remove it. And then again, the next card would be looping back to 2, and once more, we start counting from 1. 1, 2, 3, 4. 4 gets removed, and then we're just stuck on 2, so this is a sure hit. 1, 2, 2 gets removed, we win. You can tell, of course, that I was hiding my skills a little bit in the first round. So with some permutations, we will win this game. With many permutations, we will lose, but we at least get to remove a card or 2. For some permutations, we don't even get to remove a single card. If we play on this permutation, we would count 1, 2, 3, 4, game over. After that, I'm not listing any numbers that are on these cards. I'd then go 5, 6, 7, 8. I lose for sure, and don't even get to remove a single card. Of course, the reason that happens is that this is an example of what we call a derangement. Not a single one of the numbers is in its proper position. The number of derangements of the first n positive integers is often denoted like this, using the factorial notation, but on the left, it's called a subfactorial. And very interestingly, it happens to equal n factorial divided by e rounded to the nearest integer. That's pretty neat. Certainly, if the permutation is a derangement, we're not going to win the game, but as we saw, it's possible that we might be able to remove a card or 2, but still lose anyways. If you check out the Quarterly Journal of Applied Mathematics, you'll find this write-up on plane vortex motion. It looks pretty scary, but right after, we get Arthur Caley introducing the game that we've just discussed, a game he calls Mousetrap. Again, this is in 1878, and Arthur Caley, well known as an algebraist, presents this game and some critical questions related to the game that still, so long after the fact, we've yet to answer to any satisfying degree. Of course, mathematicians love thrilling games like this, especially when they're tricky to analyze. Even in this short paper, Arthur Caley made some mistakes on his mousetrap analysis. He gives a full table showing the permutations of the first 4 numbers and the cards that would get removed if we played mousetrap on that permutation. In total, you can see there are 1, 2, 3, 4, 5 permutations where we end up winning, as in all of the cards are removed, but in fact that count is not accurate. If you look at 1, 4, 3, 2, Arthur Caley has said that only the card 1 gets removed, but you can try Mousetrap yourself on this permutation, you'll actually end up winning the game. The true count is 6. So if you play Mousetrap on a random permutation of the first 4 positive integers, you have a 6 out of 24 chance of winning. That's because the total number of permutations of the first 4 positive integers is 4 factorial. 4 times 3 times 2 times 1, because there's 4 numbers that could go first, 3 that could go second, and so on. Multiply it together, that's what you get. And in total, there are 6 of those permutations, which lead to a win in Mousetrap. So again, that's 6 over 24, or a 1 in 4 chance. That's fine and dandy, but in this 1878 write-up, Cayley presents 2 questions concerning the game of Mousetrap. Number 1, for each n, find all the winning permutations of 1, 2, up through n, just like he has nearly done in this table for n equals 4, identifying those winning permutations of the first 4 numbers. And then secondly, a bit of a more granular question, for each n, find the number of permutations that eliminate exactly I cards for each I from 1 through n. Of course, the number of permutations that eliminate 0 cards is just the number of derangements, which we already know. The other possibilities are 1 through n. Of course, if we remove all n cards, we win. I want to show you a few interesting things that we do know about this simple game called Mousetrap, and we'll also look at a few more interesting questions that have popped up since that first paper. Links in the description if you want to do some further reading on the papers that have talked about this game. Remember how when we play Mousetrap, the cards that get removed, if any, are removed in a particular order. Like in this example, we would count 1 and remove that first, then 1, 2, 3, 4. 4 gets removed next, then 1, 2. 2 would get removed next, and then 3 would get removed last. 1, 2, 3, there it goes. So the order we removed the cards in that game was 1, 4, 2, 3. A simple question we might ask is it possible to construct a winning permutation where the cards will be removed in increasing order? 1, 2, 3, 4. And it's pretty easy through a sort of fill-in-the-blanks approach to see that yes, that is possible. We would of course need 1 to be the first card, so 1 gets removed right off the bat. Then we want 2 to occur 2 cards later, so we'll have to put something here, but then we're going to need 2. After that, we're going to want to remove 3, so we would count 1, and then 2, and then 3. So 3 needs to go here, thus it must be 4 that belongs here. And you could follow a similar approach with any value of n. Of course, this is the n equals 4 case, and you can see how it would work. 1 gets removed. 1, 2, 2 gets removed. 1, 2, 3, 3 gets removed, and then 1, 2, 3, 4, 4 gets removed. And thus, not only have we won the game, but we have done it in the most stylish way possible. Given how easy that was, you might be surprised that it's not possible to go in the opposite order. There's no way to arrange these cards, no matter what n is, in this case n is 4, there's no way to arrange them so that we win the game in reverse order, 4, 3, 2, 1. If that were to happen, well, for starters, 4 certainly needs to be the last card, so we could count 1, 2, 3, 4, and take the 4 out first. But in order for the 4 to be first, all of the other numbers can't be in their proper places. If any of the other numbers were in their proper places, 1, 2, 3, they would get removed before the 4. Thus, everything that precedes the 4 would need to be a derangement, like this. But this just means that once we end up removing the 4, we're not going to get to remove anything else. 1, 2, 3, nothing's in the right place, and we're doomed after that. So requiring the nth card to be removed first requires that all of the other cards are out of place. Thus, we can't win the game in reverse order. There's no obvious way known to count the number of permutations that let us win Mousetrap for a particular value of n, so the analyses that have been done are a bit more narrow. Here's some notation we're going to use. Let a nx be the number of permutations of n cards where x is the first card removed. So, for a simple example, n1 is the number of permutations of n cards where 1 is the first to be removed. How many permutations are there like this? Well, that's a very easy question to answer because in order for 1 to be the first card removed, the only requirement is that 1 is the first number in the permutation. So we count 1 and then bam, we get to remove it. All of the other numbers can be ordered however we please. We're not requiring that we win the game, just that 1 is the first card removed. Hence, the total number would be n minus 1 factorial. N minus 1 factorial is the number of ways to order n minus 1 objects, and that's what we get to do here. One object is fixed, the first card, number 1, needs to be in position 1, but all the others can be in whatever order they please. Well, that's pretty simple. Perhaps we should continue this analysis. What about AN2, the number of permutations of n cards, 1 through n, where 2 is the first to be removed? Well, just like with AN1, if we want 2 to be the first card removed, then certainly we need it to appear in the second position. We would need something first, and then we would need 2, and then everything else can happen however it does. So we would start off with n minus 1 factorial. We need that 2 to be in the second position, but all the other n minus 1 cards can be wherever they like. Though, of course, there is one exception. We can't have 1 be the first number. Any permutation that starts like this, 1, 2, and so on, we actually don't want to count that, because a permutation like this would have 1 being the first card removed. And remember, we're trying to count the number of permutations where 2 is the first card removed. Hence, we need to subtract these cases, and the number of ways this can happen is simply n minus 2 factorial, the number of ways to order n minus 2 objects, since here we're requiring these 2 objects be in these positions. But everything else, all the other n minus 2 cards, can have any order whatsoever. Now remember, the first subscript here is telling us the number of cards. If it's A5, for example, the cards go 1 through 5. And notice how AN1 was the factorial of 1 less than the number of cards. So if we wanted to, we could actually write AN2 in terms of AN1 recursively, because this here is n minus 1 factorial, which we know just is AN1, right? That's n minus 1 factorial. And then minus n minus 2 factorial, well, that would be minus n minus 1. Because again, we know that the number of permutations of n cards where 1 is the first removed is the factorial of 1 less than the number of cards. If the number of cards is n minus 1, then that would be n minus 2 factorial. And lo and behold, we can do a similar thing with AN3, the number of permutations of n cards where 3 is the first removed. We would begin by counting n minus 1 factorial, those permutations where 3 is in that third position. But then we need to subtract n minus 2 factorial. Those are the permutations where 3 is in the third position, but 1 is in the first position, and thus 3 wouldn't be the first to get removed. Similarly, though, we'll need to subtract another n minus 2 factorial for those permutations where 3 is in the third position, but 2 is in the second position. In a permutation like this, 2 would be the first to get removed, not 3. However, by subtracting these things, we've taken out all permutations that start with 1, 2, 3. We've taken these out twice, and of course we can't double count them, taking them out twice, so we need to add them back in. Thus, the last thing to do to correct this count is to add in n minus 3 factorial. Those are the permutations where 1, 2, 3 starts us off because we accidentally took those out twice, and then the rest of the permutation can be anything, but we gotta add those back in. Remember, we don't want to count permutations like these, because in this permutation, 1 is the first to get removed, not 3. However, these subtractions took permutations like this out twice, which is not correct. And from our prior equations, if we massage this a little bit, you can verify yourself that it in fact equals AN2 minus AN minus 1, 2. Sorry, I'm encroaching on some previous writing here, but let's just get to the general rule, which is that ANX, the number of permutations of n cards, where x is the first card removed, is equal to ANX minus 1 minus AN minus 1 x minus 1. So that's a pretty handy recursive formula for at least counting the number of ways that a particular card can be the first to get removed. With a little thought, we can also get another interesting formula for AN0 if we let this denote the number of permutations where 0 cards are removed, meaning that we have a derangement. Of course, we have ways of calculating that number, the number of derangements, but this is also equal to, if we want to keep it in the universe of these A's, a n plus 1, n plus 1. Because if we have n plus 1 cards, for the last one, the n plus 1th card, to be the first that gets removed, as we previously discussed, all of the numbers before it need to be in a derangement, so these things are equal. Now, of course, if any card gets hit in a game of Mousetrap, some card needs to be first. Thus, we could add up the ANX's to get the total number of permutations where any card is hit. That is, the number of permutations of the first n positive numbers, giving at least one hit in a game of Mousetrap, is this sum. The number of permutations where 1 is the first to get hit, where second is the first to get hit, and so on up through n being the first to get hit. Please note I'm using the terms hit a card and remove a card interchangeably. They both appear in the extant literature on this game. Now, similar to the ANX notation, we can use BNX to denote the number of permutations of the first n positive numbers, so the x is the second card hit after 1. Again, just to drive that point home, this notation is assuming that 1 is the first card hit, and we're counting permutations where x is the second card to be hit. And in fact, this ties directly to the A notation that we just discussed. This is equal to a n-1 x-1. If 1 has already been hit, then one of the cards is gone. We have n-1 cards left, and so these counts are equivalent. You may think they feel quite different because in BNX, we're assuming that 1 has already been hit, and we have this card n. Whereas with an-1 x-1, 1 could still possibly get hit or not get hit, and we don't have the card n. But in fact, 1 and n are playing very similar roles here. If I'm looking at a permutation of the first n-1 numbers, 1 would have to be the first card for it to get hit first. Similarly, if I'm looking at permutations where 1 is the first number hit, then n is going to have to come right after in order for it to get hit. If 1 gets hit first, then it must occur first, but if n is going to get hit, then it must be first in what comes after. That's because if there are n cards total, and we've already hit 1, well then there are n-1 cards that remain. After eliminating the 1, we would start by counting 1 on n, if n was here. We'd count all the way up through n-1 until finally looping back to n, where it would get removed. Just like how when we're looking at these permutations, 1 has to occur first to get removed first. Over here, n has to occur first after what we're already assuming is there in order for it to get hit. So these permutations kind of don't have 1 because we're assuming it's already been hit and we're looking at what happens next. And these permutations certainly don't have n, but in fact n and 1 are playing very similar roles, and these numbers are equal. And just as with the A's, we could add up these B's in order to get the number of permutations of n cards where at least 2 numbers are hit and 1 is the first that gets hit. In this case, we start at BN2 because remember, we're counting permutations where 1 is the first number hit. So all of these have 1 as the first number hit, so we start by looking at where 2 is the second number to be hit, and then where 3 is the second number to be hit, and so on. Add all of these up, you get the total number of permutations where a second number is hit after 1. And of course, thanks to this equation, we could write this sum as well in terms of the A's, just like that. We could also analyze a similar thing denoted CNX. This counts the number of permutations of n cards, where x is the first to be hit after 2 instead of after 1, as in this notation. So with this notation, we assume that 2 is hit first, and we're counting the permutations where X is hit next. The analysis with this starts to get a bit messy. I'll leave that for you to check out if you're interested. Again, links in the description. Relating a bit to some of the discussion we had earlier, Richard Guy and Richard Nowakowski introduced something related to Mousetrap called reformed permutations. These are orders of numbers that result from a winning game of Mousetrap. We saw earlier how it was easy to construct a permutation so that we win the game in order 1, 2, 3, 4, but it was not possible to construct a game where we win in the reverse order. So this would be a reformed permutation, but the opposite order would not be. That then leads to the question of characterizing these reformed permutations, a question for which we do not have an answer. We can say a few things, like I just said, a reformed permutation can't go in the reverse order. In fact, it can't even start with the biggest number. Again, if we were playing a game of Mousetrap with, say, n equals 6, if we want 6 to be the first number removed, all the numbers before 6 have to be out of order. Maybe we would have 2, 3, 1, 5, and 4. In this case, 1, 2, 3, 4, 5, 6. 6 is the first to get removed, but then nothing else will get removed because none of these numbers are in their proper location. So a reformed permutation cannot start with the biggest number. But the identity permutation, where all of the numbers are in their proper order, that is always a reformed permutation. For example, in the case of n equals 6, we can obtain that identity as a reformed permutation by playing Mousetrap on this permutation, 1, 4, 2, 5, 6, 3. If we play Mousetrap on this permutation, 1 is the first number to be removed, and then 1, 2, 2 is the second to be removed, and then 1, 2, 3, 3 is the third to be removed, looping back, 1, 2, 3, 4, 4 is the fourth to get removed, and then 1, 2, 3, 4, 5, and then 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6, we get the identity as a reformed permutation for this game of Mousetrap. Of course, since Mousetrap is played on permutations, if we get a reformed permutation, we could try playing Mousetrap on that as well, and in this way, we could potentially link winning games together. It's like stringing together an ultra combo. Consider this with n equals 4. This is a winning permutation for Mousetrap. If we play on this permutation, we get 1, 2, 2 gets removed first, and then 1, so 1 gets removed next, and then 1, 2, 3, 3 gets removed next, and then 1, 2, 3, 4, 4 gets removed. This is a reformed permutation, and we could play Mousetrap on this as well. That would give us 1, 2, 3, 3 gets removed first, 1, 2, 2 gets removed, 1, 1 gets removed, 1, 2, 3, 4, 4 gets removed last, and then this is where the winning ends because this is not a winning permutation. But we at least see the potential for these reformed permutations to link together. That then gives us another question. For given n, what is the longest sequence of reformed permutations? Are there sequences of arbitrary length if we're willing to increase n enough? Are there cycles other than these two? We call these cycles because they loop, though of course they happen to be quite trivial. This a cycle with n equals 1, and this a cycle with n equals 2. These reformed permutations just lead back into each other. The answers to these questions are not known, but the same authors who introduced reformed permutations introduced this interesting variation of Mousetrap called Modular Mousetrap. Here's an example of Modular Mousetrap with n equal to 5. So here's a permutation, 1, 3, 5, 4, 2. We would count 1, and 1 gets eliminated, then 1, 2, 3, 4, 5. If this was normal Mousetrap, our next number would be 6, and you see that we would then be hopeless. We're never gonna hit another number. But in Modular Mousetrap, we start counting back from 1 every time we hit n. So we would count 1, 2, 3, 4, 5. 5 is n in this case. So then we would actually go to 1, 2, 3, 4, 5. 5 gets eliminated, the game actually continues. 1, 2, 3, 1, 2, 1, 2, 3, 4. It's a winning permutation with Modular Mousetrap. In fact, in this case, where n equals 5, a prime number, the situation is very simple. If we're looking at a prime number, then we're either going to have a win or a derangement. So if we have a permutation of a prime number of cards, either all of the numbers are in the wrong order, and so we will eliminate none of them, or at least one number is in the right place and will actually end up eliminating all of them and winning the game. You could try Modular Mousetrap on this permutation. Since it's not a derangement, guaranteed you're gonna win this game. And that's because prime numbers have no factors, so if you're able to eliminate a single number, like here we see we eliminate 3, well now we have 6 numbers remaining, but we're counting up to 7. 7 has no factors in common with 6, and so there's never going to be a sort of looping situation where we keep skipping over certain numbers. This is in contrast to a composite number like n equals 4. This permutation, 3, 2, 4, 1, isn't a derangement. However, we would not win this either playing Modular Mousetrap. We would count 1, 2, 2 gets eliminated, then 1, 2, 3, and 3 gets eliminated, but 4 has 2 as a factor, and so you can see the difficulty this causes. 1, 2, 3, 4. And then we loop back to 1. 1, 2, 3, 4. 1, 2, 3, 4. We're stuck. We're not hitting anything. This problem doesn't occur with prime numbers, so as long as we're able to knock out one number, we'll be able to knock them all out when n is prime. Another interesting thing you can check out with Modular Mousetrap is that the identity permutation actually is a 1 cycle in this game. That means the reformed permutation that we get from the identity permutation is itself. Check it out. There's 1, okay, so that's where we start. Then 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2. 2 is next. And this pattern continues. I'll leave it to you to verify. So the question about different cycles existing besides these trivial ones, well, at least we can say the situation is a bit more interesting in the case of Modular Mousetrap. Just like with normal Mousetrap, in the case of Modular Mousetrap, there are not only cycles, like this interesting identity cycle, but there are also paths, which could eventually end in a derangement. For example, just finishing looking at the case of n equals 3, a prime number, which means every permutation is either going to be a derangement or a win, there are only 6 possibilities. One possibility is the permutation 1, 3, 2, the reformed permutation of which, after you play Modular Mousetrap, is the identity 1, 2, 3, which we know cycles into itself. Another possible permutation that is separate is 3, 2, 1. This is not a derangement. 2 is in the proper position, so we know that it's in fact a winning permutation, the reformed permutation of which is 2, 1, 3. 2, 1, 3 is also not a derangement, so this is also a winning permutation, and the reformed permutation is 3, 1, 2. This is where the sequence stops because 3, 1, 2 is a derangement. This covers 5 of the 6 permutations of the first 3 numbers. The one other permutation not here is another derangement, 2, 3, 1, which just stands alone. So with Modular Mousetrap, we see that we have cycles of length 1 or 2, depending on how you count it, and we have a sequence here of length 3, here of length 1. This leads to our final question we might ask: are there k cycles or paths for every k, a cycle or path of every length? What's the smallest n which would yield such a cycle or path? Could we get cycles or paths of arbitrary length if we were willing to make n big enough? These are just a handful of the interesting questions regarding the permutations that result from the game of Mousetrap. And again, very little is known about all of these questions, so I thought it would be fun to talk about. Let me know in the comments if you have any questions. If you like what I do, consider joining the channel for lots of exclusive videos and music and all that fun stuff. And be sure to subscribe for the swankiest math videos on the internet.
I'm unstable, feeling hard to keep the cable cut and untuck the cable. Texas Instruments don't reply, I think this time it might be fatal. Wish to sell my own fake, cause I'm jaded. Hate the odds that I calculated. Press and pull and pray and push it all the way until the whole blue planet faded. Psychosomatic habits, why you so